Hello everybody and welcome to the March edition of the Royal Astronomical Society's public lectures. My name is Dr. Sheila Kanani and I'm the Education Outreach and Diversity Officer here at the RAS. And today we've got Dr. Jenny Carter with us. Dr. Carter is a Royal Society Dorothy Hodgkins Fellow. She's at Leicester University and she's heavily involved in the SMILE satellite, which is expected to launch in 2024. She's a Women in Science Rising Talent and she's a Caroline Herschel Prize Lecturer for 2021. We will be having a question and answer session at the end of the talk, so feel free to post your questions into the Q&A function on Zoom or on YouTube if you're watching on YouTube. And without further ado, I pass you over to Dr. Carter.
Thank you, Sheila, for that nice introduction. I'm just going to share my screen now. And here we go. Will you just confirm that you can see that, please?
Yep, that sounds good.
Brilliant, thank you. Well, thank you everybody for coming this afternoon. I'm excited to have this opportunity to speak to you about space weather. This is the relationship our sun and our Earth have together. And later on in this talk, I'll talk about how we're going to investigate space weather with a mission called SMILE. SMILE is due to launch in 2024, and it's being prepared by the European Space Agency and the Chinese Academy of Sciences. It's a joint mission, and it's only a couple of years until we have to launch, so really it's all hands to the pump with SMILE. So I'd like to start with this image of the Aurora Borealis, as I think the aurora are the best way that we can consider space weather for us living here at the surface. And this picture was taken up in Shetland just a couple of days ago. So space weather can be seen from the UK. And if you're lucky to be up in Scotland, Northumbria, for example, or Cumbria, or Northern Ireland, you might have had the chance to see these aurora on multiple occasions. So we do experience space weather here in the UK. I gave this lecture in November to the Herschel Society, as this is a lectureship that is in memory of Caroline Herschel. Now, Caroline Herschel was a German astronomer, but lived much of her life in the UK. And she was based around Bath and then near Slough and Windsor. But for her, space weather was a bit of a problem. So space weather can be problematic. And so back in the 1783, Caroline was trying to make some observations of astronomical observations, and she didn't want any of this space weather. And she notes in her diary and her observation notes that there was these extremely strong northern lights. And she goes on to say that these were unfavorable conditions. So this really, really messed up her observing. And I had this wonderful opportunity to see these notes hold them in my own hands at the Royal Astronomical Society. So I'm very grateful for that experience. And I hope that for me, this has started this lifelong love of history of astronomy and really getting to the human behind those astronomers that we read about and their discoveries back several hundred years ago. So Caroline found that this space weather was a problem. And then she continues to say a few days later that these northern lights are still there. So this is a big event. Given that she lives in the south of England, we don't often see the aurora down in the southern bits of the UK. But what is this space weather? Well, collectively, we think of space weather as this group of problems that we can have. Now, this is the sun interacting with our Earth and our Earth's magnetic field and the atmosphere. So we can have problems with satellites, spurious signals, for example, in satellites. This can cause problems with communication systems, which then in turn cause problems with logistics. And we can also induce currents in long power lines, for example, or anything that acts like a wire, for example, a railway line. So there's a range of different problems, and they're often sort of compounded. And we live in this highly technological age at the moment. So this is where space weather is really going to kick in as a problem. It's kind of, in that way, a newish problem for society. So one of these problems is these ground-induced currents. So when the solar wind and the sun, which I'll describe in a minute, interacts with our Earth's magnetic field, and we can have currents, electrical currents set up in near-Earth space. And we can have these currents along the ground, and these can cause problems. We can also have incredibly bright aurora, and the big space weather event that people talk about is back in 1859, the Carrington event. And this caused, people saw aurora that were bright red. Obviously, this isn't a picture from that time, but these red aurora were seen down as far as Texas, Florida, and Mexico. So this was a very dramatic event. I have been cautioned, though, recently that although we can think of these dramatic and problematic events for society, we shouldn't really scaremonger the public. And when I heard this at the European Space Weather Week back in Glasgow in October, it brought to mind this film called Knowing with Nicolas Cage. And I don't know if you've seen it, it's an old film now, but humanity was wiped out by a great big solar flare. And so I don't want to end up scaring anybody, but it's a problem that we need to quantify and therefore know how to mitigate against. And the UK government is doing this. They have produced a document about this preparedness strategy, whereby various stakeholders are looking into how to prepare our systems in the event of a large space weather event. So the Met Office runs a prediction centre, and you can see an operator here looking at multicoloured images of the sun and looking at whether we can track features on the sun and see how long it's going to take for that feature to affect us here on Earth or at all. And then various stakeholders like the National Grid will take that information, and then they can prepare for the most severe events. So this all comes back to our sun, and I'm just going to run a movie now. This is a movie taken by the Solar Orbiter fairly recently. And this is a mission that is on its way into the inner reaches of the solar system. I wanted to show this movie because it shows how dynamic and violent processes are going on in the sun. And the sun turns around quite quickly. It's taking about a month to rotate here. Some astronomers that I know at the European Space Agency were telling me that this is an unprecedented level of detail that we're getting of the sun with Solar Orbiter. It's about halfway between the Earth and the sun at the moment. And they're really pleased. They haven't actually released this incredibly high quality data yet, but they're excited about how that they can link up behavior that you're seeing there with all these flares, these bright bits, these very active regions, with what's going on at the spacecraft, and then make better predictions about what will happen at Earth using this information. So what people do who are wanting to look at space weather, they take images like this from the sun, and they want to track these large features into the solar system. So I'm going to show you a movie, and we're imagining we're looking down onto the sun, and we've got the solar system around us. So this is an Enlil simulation. Now you've got two panels there. One's looking at the solar wind density, and one's looking at the velocity. Now this solar wind is coming out of the sun at all times. It's a bit like, and you can see it in this sort of pinwheel effect, it's a bit like a hose being thrown around. The solar wind's mainly made up of protons and electrons, and on average it travels about 400 kilometers a second, and so on average it would take a couple of days to reach the Earth. So you can see that there's this hose pipe effect that we can see in these pinwheel effects, and there's a little cut through, the little green little blob that you can see there is the Earth. So these are models and predictions that scientists use to predict how dense the solar wind will be when it hits the Earth. Now I'm going to show you another movie from the Enlil simulation again, but this time there's another structure embedded within the normal solar wind that's being thrown out by the sun at all times. So if we run this movie, which hopefully it will run, I'm getting the keynote wheel of doom. Oh, here we go. Oops, missed it. I'll try again. It's click. Here we go. Right now, here you can see that there's an additional structure that's coming out into that solar wind. Now, this is a large cloud of plasma, this highly charged electrons and protons mainly coming out of the sun in this big cloud on top of that normal solar wind, and it acts a bit like a snowplow. It's going to hit into that normal hose pipe and go through the solar system and eventually hit Earth. Now we call these coronal mass ejections, and these cause us the biggest space weather events at Earth. And what's happened when they get to Earth? Well, they encounter our magnetic field. Now, this is a kind of noddy diagram of what the magnetic field of Earth would look like. And you can imagine when you're at school, you might have taken a bar magnet and sprinkled some iron filings over that bar magnet, and you would have seen a pattern much like we see here. Now, when the solar wind encounters this magnetic field arrangement gets squashed and squished around. On the day side, where the solar wind's coming in, then the magnetic field gets very, very squished. And on the night side, then this magnetic field gets really, really drawn out. So we have this compressed day side and a stretched out night side. So we'll see this in this movie here. This is a simulation, and I think it's important to note these are movies. And because it's very difficult to image this whole system, which we'll talk about later on. But in here, you're seeing the solar wind coming across through the solar system. We're ignoring the couple of days it takes to get there, and it's interacting with our Earth's magnetic field. Now, in doing so, something can happen on that day side, and this movie will run again so we can see it in a second. Magnetic reconnection can happen on that day side. Now, we're on Zoom, and if I'd given this lecture in person, then we'd expected some audience participation. My old boss at the University of Leicester, I'm now a fellow, so I don't know, I will always think of him as my boss, but he loves this analogy of a Tai Chi movement. So we stretch our arms out here, magnetic reconnection can happen on the day side here, and we can pull over those field lines, and they can reconnect on the night side again, and they're going to ping in together, and in doing so, they stretch out. So you can do this at home, and it's a great way of remembering what happens with the magnetic field lines of Earth. And in doing so, when those magnetic field lines can reconnect on the night side of Earth, they can send in some of that solar wind plasma to the north and the south. And that's why we get this ring of aurora in the north and the south. And you can see it doesn't sit at the poles. So if we look at those aurora that we're creating in the northern hemisphere or the southern hemisphere, but one hemisphere, we can see that we don't have aurora in one place. We have this ring, and we call this the auroral oval. This oval these images here were taken by a satellite that hasn't been operational since 2005. So it's a long time since we've been able to take images of the aurora. And you can see that there's lots of substructure in there. There's lots of things going on. So this is useful information to understand what's happening between the Earth and the solar wind. So we know that this is another schematic of the Earth's magnetic field, and I've put this in here because it really shows the 3D nature of that structure. And we sometimes liken it to a bullet, say like when you see from the Matrix movie, and you can see the supersonic flow, and then it goes to subsonic flow, and you can see the structure around it. Or another way of thinking it is a bubble in a stream, that it's getting buffered and it's getting changed in shape at all times. Now, if we took that magnetic field and we took a slice through it and we drew that magnetic field, we might get a sketch like this. So you've got the solar wind coming in from the left, and then we have our magnetic field. And the solar wind is highly variable. We saw in the simulations before that it can change in density and velocity very quickly. And as it does so, then this magnetic field of the Earth is going to get squashed. And we call the boundary between the solar wind's magnetic field and the Earth's magnetic field the magnetopause. And that's marked with this cyan light blue label, an arrow, and that dashed line. And we want to measure how far away that magnetopause is. So we have this day-side reconnection that we saw in the video, and the night-side reconnection as well. We know this is going to change on about minute time scales, or roughly, or we think it does, because the solar wind changes on that kind of time scale. Now, if we look at that magnetic field from the front, or we look at the Earth's magnetic field, we might see something like this. So we've got the north at the top and the south at the bottom. Now, the solar wind itself is this electrons and protons plasma. It's actually carrying with it its own magnetic field. And we're going to drape those field lines from the solar wind over the Earth's field. So we have those in blue, and these are the solar wind magnetic field lines. Now, where we have roughly anti-parallel field lines, we have the Earth's magnetic field pointing this way, say upwards, and then the solar wind pointing downwards. That's where we'd expect magnetic reconnection to happen, and this opening out of those field lines that we saw in the movie before. So we might expect reconnection around this whole region across the front of the Earth's magnetic field. So from this viewpoint, you're in the solar wind and you're looking at the Earth. Now, this magnetic reconnection is setting up currents in the Earth system. And this is sort of the physicsy bit for those that would like to do this with me. You have a wire. You can pretend you've got a current along the wire. For here, we're saying there's currents flowing along this wire, and the magnetic field line is associated. There's magnetic field associated with that current, and we think of this as this right-hand rule. I don't know if you remember this from your physics. Well, what this does, this right-hand rule physics and this extra field that we're creating, it causes deviations, changes in the Earth's magnetic field, and we can detect these down at the ground. So this is a movie looking down at the northern hemisphere, and you'll see some green blobs on that map. Now they're going to show us how much of that deflection that we saw in the magnetic field is caused by the currents that are flying up in space because of the magnetic field that's associated with them. And you'll also see some aurora kicking off, and you'll notice that here we have a good association between those green deflections in the magnetic field and the bright aurora that's also been plotted in the same section of looking down on the northern hemisphere. You see Greenland, so we're just over Greenland, and we can see it's all kicking off in this region here with these long green sort of flagpoles and the bright aurora that we're seeing underneath. So that's a way of detecting what's going on in space, is using these magnetic deflections. But we do want to go and investigate space weather, and we can do that with, we have loads and loads of spacecraft. This happens to be a NASA composite of a schematic of the missions they have out there. The one thing I want to note about all these missions is, well, the majority of them are what's called in situ spacecraft. They are taking measurements immediately around the spacecraft's surroundings. But we don't have a really good understanding of the large scale structure of this. Those spacecraft that we saw before, they take very precise measurements exactly where they are in the system, but they don't have this overview of what's going on. There's a reason that this is only a sketch. We've only got a sketch of this magnetic field. We don't have a picture of it. And there's a couple of important questions that we can ask. So what is that 3D shape of the magnetopause, the frontier between the solar wind and the Earth's field, and how does it move? So this is a graph showing how the magnetopause may move in response to that magnetic reconnection with the solar wind. It may move into the Earth, closer to the Earth, really fast, and have this step down over time really quickly. It may take ages to move in and move, or it might take a kind of jumpy, bursty move in various steps. So we don't know how the magnetopause moves on the large scale. And it's important to understand this reconnection. You think, oh, who cares? Why do I care what the magnetopause is? Well, understanding this process of reconnection, where the solar wind reconnects with the Earth's magnetic field, is key to understanding how the energy and momentum are transferred between the solar wind and the Earth system. It's a real door to our atmosphere. So this reconnection and these particles can come in, and then we can have interactions with the lower atmosphere. Similarly, processes in the lower atmosphere can affect what's going up further up into the atmosphere and into, getting into 200, 300 kilometers. So there's a complicated systems of feedback between these regimes, lower atmosphere and upper atmosphere, and then up into space that we need to understand. And we can understand what's going on in space by using a process called field line tracing. Now, if you imagine you've got that sketch of the magnetopause, if you took a field line and you look at the red arrow here, and we draw back towards our atmosphere, or what we call our ionosphere, which is an upper region of our atmosphere, then we can look at our ionosphere and see what's happening there and see, well, maybe it's giving us these footprints of what's happening out in space. So we can learn about what's happening out in space by looking at our upper atmosphere. And we can do that by using this remote sensing technique, or field line tracing, and use spacecraft to maybe look down one of those magnetic field lines and have radar looking up, and we can make common measurements in that sort of area of our upper atmosphere and see what they're going to tell us. So we might have a spacecraft that's looking down the field line, seeing what's happened as it goes over the auroral oval, for example, or the northern regions of the Earth. And then we can look up using equipment like this. So we have the IceCat radar here. This is a radar that's on Svalbard and taking measurements of the atmosphere. or the SuperDARM radar, which is a consortium of radar across many countries that's looking at seeing what's happening in the atmosphere. And we as scientists get pictures like this. So imagine again, you're looking down at the Earth in these images, and you're looking at some part of the atmosphere. So on the left, we have images from the Aurora. These are taken from space looking down, and you can see that we can look at bright regions, less bright regions, and get some understanding of that interaction out in near-Earth space. And then this bottom example on the bottom left is another image that we've used in the past to look and see what's going on with those aurora and what they can tell us. On the right, you can see some coloured regions, and they tell us how fast our upper atmosphere is being stirred by the opening and rearranging of those field lines that we saw in the movie. And the red ones, that it's going really, really fast. So this is at the top, this is towards the sun, looking down, and we can see the red regions really fast, that the ionosphere is being stirred quickly in this region. So there's lots of different ways that we can try and understand what's going on in space using information from our atmosphere. And just on the side, looking at Caroline again, she continued to have problems throughout her career with space weather. So the first snippet I showed you from her diaries was from 1783. Now, a couple of years later, she again quotes that the aurora is problematic. It's a very strong Aurora Borealis. So she's changed name. She used to call it the Northern Lights, and now she calls it the Aurora Borealis. She can hardly see the object any longer. So again, space weather is causing a problem for Caroline. So this is our sketch, and I said before, this is only a sketch. We know more about the interaction with stellar winds with other astronomical objects through images like this, and we haven't got an image of the Earth system. So this image you see in the bottom right is from the Hubble spacecraft, and it's taken an image, and you can see this shocked region of the stellar wind being deflected around the bright object in the middle of the image. Now, we haven't got an image like that of the Earth system, and that's crazy. We're in the best laboratory that we have, which is our own Earth. So we'd like to go and do that. And this is where SMARL comes along. But SMARL is a mission that is going to try and take images of the Earth's magnetic system. But the origin of SMARL as a mission comes from a kind of weird place. I used to be an X-ray astronomer before I started working in solar-terrestrial physics. And so this is a little journey through how X-ray astronomers became solar-terrestrial scientists and how two fields can really help each other out. So back in the 1990s, there was a mission called ROSAT, which you can see here on the left. Now, ROSAT went in orbit around the Earth at a low Earth orbit, and it was making this large-scale studies of the X-ray sky. Now, the X-ray astronomical sky is really looking at the most violent parts of the universe, and X-ray astronomers are looking at black holes and really hot gas. This is what ROSAT wanted to do, make a great big survey of what was going on out in the X-ray regime in the sky and take a picture of the whole of the sky. When it was doing that, it also wanted to look, it looked at the moon just for fun. And here's an image of the moon, and you can see that you've got the bright hemisphere of the moon where sunlight's coming in from the right. Now, on the other side of the moon, we'd expect it's completely dark, but you can see that there's these bright pixels that are glowing, they're orange. And it was a real mystery, why would that be? We didn't expect any X-rays to be reflected off the surface of the moon on the night side. There's no reason that we'd get X-rays from there. So this was a mystery back in the late 1990s. And at the same time, ROSAT was making this picture of the entire sky. Now you can see lots of bright bits and darker bits, and this is the astronomical sky. And it did, and the ROSAT team published this amazing picture. Now, but before they got to that picture, there was this picture, which is obviously not as good quality as the upper picture. And you can see that instead of having this lovely picture of the X-ray sky, we've got a picture with streaks along it. You can see almost, you can imagine where the satellite was going on its orbital tracks. Why is it all really streaky? So the question is, what are these streaks. So we've got two problems with the ROSAT data. We've got the moon problem, and we have these streaks in the X-ray data. Now, there was a guy called Tom Cravens in the University of Kansas, looked at the times when ROSAT was taking those measurements with the streaks in it, and plotted the count rate of X-rays against time, and also what the solar wind was doing at the same time. And you can see from the graph here that they're very well correlated. So when ROSAT sees these strange streaks in the sky and peaks in the X-ray counts, then the solar wind is really active, has high flux. So we've got lots of solar wind at the same time as lots of X-rays. And this was a golden era for X-ray astronomy. So that in 1999, there was a European Space Agency launched an additional telescope called XMM Newton. And it's still going, actually. We had a 20-year anniversary a couple of years ago. It's a massive telescope. So ROSAT was quite small. And then XMM came along and was massive and was taking pictures of high energy astronomical objects as well. Now, some of the same team worked on ROSAT and on XMM. And I just wanted to credit some of my colleagues in the XMM team. So I'm there somewhere. I used to work on this mission at the European Space Agency, and then when I moved to Leicester. And some of the people here used to work on ROSAT as well as working with XMM. They're a great bunch, and we had lots of fun working on XMM. But one of those colleagues, Steve Snowden, who's been a really important mentor to me in my life, he's now retired. He used to work for NASA. He worked on ROSAT, and he's the man that made those maps of the all X-ray sky earlier on and saw those streaks. He came, I remember on a meeting, he drew the first picture of the Earth's magnetic field that I was aware of. And he also worked on XMM, and we were having this problem with XMM that we were seeing a bit of extra signal, and we didn't know what was happening there. And XMM had this crazy orbit, or has this crazy orbit, where it goes about 120,000 kilometers away from the Earth, spends a long time. It takes about 2 days to orbit the Earth, and then it zips past the Earth and it goes around again, this really elongated orbit. Now, sometimes, depending on which way that orbit is orientated, XMM can look at the Earth's, look through the Earth's magnetic field. So what XMM is doing when it's looking at a star or a galaxy a long way away is having to look through various different bits of the sky that it doesn't really want to look at. So as astronomers, we need to clean up our data and get rid of these. So you can imagine what you want to observe is this bright object some far away in the galaxy or even beyond our galaxy. And you have various different X-ray sources that you're looking through. So this is foreground emission. So you have the local bubble, you have the heliosphere, which is the rest of the solar system can glow a little bit in X-rays. And you have the exosphere. Now, this is the region of near-Earth space. The exosphere is around us. It's a big cloud of hydrogen. And so it turns out that these pesky streaks that we saw before in the ROSAT data, and also those night side emissions that we saw in the ROSAT data, are due to the exosphere glowing in X-rays. And nobody had considered this when we launched XMM. XMM was for X-ray astronomers. No one really cared about what the Earth was doing. They were looking at stars and galaxies. So this foreground emission really had to be understood. And this is why I did my PhD, looking into how much of a problem is this foreground emission that is affecting XMM Newton's observations. So why would you expect X-rays from Earth? It seems a bit crazy. So if we go back to our sketch of the Earth again, you've got the magnetic field. But if we ignore the field for now, we can think of the Earth as sitting in a potential well of gravity whereby there's a cloud of hydrogen around it. In 3 dimensions, a big cloud of hydrogen. This is neutral hydrogen. It's not doing anything. It's not affected by the magnetic field. But we know we've got the solar wind coming in from the left. Here we've got the solar wind, which we know is generally electrons and protons, about 98% electrons and protons. But a very small percentage of that solar wind is made up of highly charged oxygen, carbon, say, nitrogen, neon. So we have these extremely highly charged ions. And by that, I mean, you've got your atom and you've stripped away all of the electrons from that atom, and you're left with a nucleus, maybe one electron if you're lucky. So you've got oxygen, we call that oxygen 7+, oxygen 8+ if it's got no electrons left. And so this exosphere is this hydrogen cloud, which again is difficult to really appreciate because we've only got one photo of the exosphere that's ever been taken. Now, this was taken from many thousands of kilometers away from the Earth, looking back at the Earth on a Japanese satellite that was going to do something else. It was actually looking at improving some technology. It was a sort of test mission, but it did have a chance to look back at the Earth, and it took this one-shot image of that cloud of hydrogen. So we can see that there's a big cloud of hydrogen around the Earth, and that's our exosphere. That's in it's called Lyman alpha emission. It's an ultraviolet emission. But so this and this exosphere here that we can see in the sketches, that kind of rough greeny area, is the reason why we're getting X-rays. And this happens because the solar wind can go through a process called charge exchange with that exospheric hydrogen. So with that, we have the oxygen, say, coming in from the solar wind, encounters that hydrogen in the Earth's exosphere, and it steals an electron. Now, that electron is in an energy state that's not very stable. It's not going to be there for very long. And when that electron relaxes, then into the atom, we have a photon released. And that photon happens to be in the X-ray regime. And we call this solar wind charge exchange, or SWICS. So this is going to happen with oxygen and carbon, say, and give us a photon that is characteristic of the ion that's come in. So we know from that energy of the photon whether it is from oxygen or whether it is from carbon. So we have this solar wind charge exchange process, which we call SWICS for short. It's a lot easier to say. And it's going to be dependent on how much of the oxygen we have, how much oxygen we have in the solar wind, how much hydrogen we're going to see how much X-rays we're going to get. So there's some questions that we don't really understand yet, and these are current questions within the field. What is the composition of the solar wind? That's going to change the number of X-rays we get, and how much hydrogen is actually in that cloud, given it's quite difficult to measure and we've only got that one picture. So we've got the scenario here, we've got that oxygen carbon coming in the solar wind, encountering this cloud of hydrogen. But then if we mix the two together, we'd expect the X-rays roughly from this region here that you can see in the pink. So that is what ROSAT and XMM are both looking through. And this is where we get those X-rays from the exosphere. Now, XMM wanted to look at, especially for the astronomers in the audience, people in astronomy are very familiar with this image of the Hubble Deep Field. XMM did this, it looked at the Hubble Deep Field. It's a great source for calibration for astronomers. And this is a nice Hubble image of it, so we don't get anything like this with X-rays. But we can get some spectra from it. So XMM went away and looked at the Hubble Deep Field, and it looked at the Hubble Deep Field 4 times. In doing so, 3 of those 4 times, XMM saw exactly the same spectrum, and you've got the spectrum here in the bottom panel. So we have energy, flux versus energy, and you can see that all these points are lined up over each other, and this is our X-ray spectrum. And you can see the fourth observation of the Hubble Deep Field using XMM was different. Now, there's no reason why that Hubble Deep Field should change in X-rays. We're not expecting any variability from that part of the sky. But you're seeing these lumps and bumps in the black that you can see in the bottom graph that weren't expected at all. And the person, giving credit to the person who did this, it was Steve Snowden, who was the person of the ROSAT maps and who also first started talking about the exosphere as a problem for XMM Newton. So those are those extra spectral lines that we weren't expecting. So can this SWICS emission therefore be used to study the solar wind, these X-rays that we're getting? Well, if we look at the sun on a particular day, this is a day that I was interested in, this is sunny, you can see some active regions here. In my PhD, we did this study whereby we saw a CME, or we think we saw a CME, with XMM data, and I'm just going to take you through that now. So that was from our simulation. We see that these CMEs coming up from these very bright regions of the sun. They can then go along and hit the Earth. If we look at something like this in XMM, we can use a couple of spacecraft to look at what's going on in the solar wind and then see what happens in XMM. So we had a look on over time to see, we saw a spacecraft called ACE saw a really bright signal in the solar wind. Slightly before, another spacecraft called WIND, a bit later, saw another bump. You can see that there's a little shift between the two light curves here. And then if we look at this data with XMM, we see this, this bump even later. Now, XMM is quite different from those other spacecraft. So ACE and WIND are both in situ spacecraft. They're measuring exactly the solar wind that's coming and hitting them. Whereas XMM, we know, has this view looking out. It's a pencil beam image, and it's looking out into the X-ray sky. So they're different ways of looking. But we did see this bump in XMM data. So we think we saw the CME hitting ACE, hitting WIND, and then XMM noticed this as it was looking out into the faraway astronomical sky. If we looked at the spectrum from this XMM study, then we saw this spectrum here, and there's various different components there, but I just want to point out that we have detected in this observation all these different ions. So we've got oxygen 8+, oxygen 7+, carbon, nitrogen, neon. So there's a load of ions there that we didn't expect to see, and we detected with XMM. So the point really to take home from this is it's a novel way of using an X-ray telescope when we didn't expect to use XMM in this way at all, and use it to look at the composition of the solar wind. So could X-ray astronomy help with imaging the Earth's magnetic field? And the answer is then yes. And this is where the idea from SMILE came along. Now, SMILE isn't the first try that we had at designing a mission to use X-rays to look at the Earth's magnetic field. We first had this mission back in 2007-ish. It was a NASA mission to go back to the moon. It was called MAGEX. And I think this is a story of perseverance in the space sector. So astronomers come up with these ideas and they have to try again and again to get their ideas accepted by the agencies. So first we tried with NASA, a mission called MAGEX. We had Axiom with ESA, got rejected. We went through with MAGIC, with NASA again, got rejected. We changed Axiom, made it a bit smaller, a bit cheaper, and got rejected. And then suddenly in 2015, we changed the mission name to SMILE, a lot happier, and we got selected by the European Space Agency and the Chinese Academy of Sciences. So this is what SMILE is going to do. SMILE is going to look down at the Earth's magnetic field and take 2 images, and it's going to do this simultaneously. So SMILE has this long acronym, Solar Wind, Magnetospheric, Ionospheric Link Explorer, and it's mentioning the magnetosphere and the ionosphere because it's going to take 2 images of that. It's going to take the magnetosphere image and then the ionosphere. And you can see this with these blue and the purple triangles in the image there. Is have 2 cameras on board. One of them is in X-rays, in that looking in that blue area, and the other one is going to use ultraviolet emissions from the aurora to look and see what's happening in the ionosphere at the same time as seeing what's happening as that solar wind's coming in and slamming into the Earth's magnetopores. So we're going to get something like this. We're going to get an image from that X-ray camera. It's going to see where that magnetopore's boundary is, and at the same time, we're going to look at that aurora over from space. And this is a novel idea. This is quite new in space weather physics. Most people do those in situ measurements. We're going to actually take images. And the X-ray camera is inspired by nature. So the X-ray camera is being developed by the University of Leicester, but in partnership with many institutions around the world. And the X-rays are going to be focused using what's called a lobster eye optic. Now, you see some images there. There's a lobster eye and then a zoomed in one with a microscopic image of it. Now, what we've done is we've copied that in a laboratory, and you can almost copy the lobster eye. Now, a lobster lives in the bottom of the ocean or in low light levels in water, it doesn't get very much light to come in, so it needs to collect as many as possible. And that's the problem with X-rays. We don't actually have many X-rays, so we need to collect them as well as we can. And so we can copy that in glass. So you can see on the top right, you can see these pores. We call this a micropore optic. And we've copied that lobster eye to see if we can focus X-rays. And you can see we can make those little pores into plates. Now this is a couple of centimeters across. And if we stack up a couple of those plates, then we can use that as the optics part of our telescope. So we can have X-rays coming in, they hit this grid of these micropore plates, and then they can get focused on a detector behind. And so this is how we're going to take our first pictures of the magnetopores and the magnetosheath and see how it reacts. And we'll get something like this. And this is what this X-ray camera looks like at the moment. Now, this is a movie here. I'll just keep playing that. That's from some testing that we ran last year on the structural thermal model for the camera. So we make a model of the camera, real size, and it gets shaken. You can see it's being shaken on a plate to see if it's going to survive launch and vibration testing. And that was done last May. And then you can see the engineers here on the top, that's the University of Leicester, and they're preparing. You can see how big the camera is. It's not very big, it's about 1 meter tall, and it's very lightweight. Those optics are really, really light. That's the benefit of them. Light means cheap when you go into space. You can see how big it is, and you can see down the same model down in Spain, Airbus, where it's been wrapped up in some foil to do some thermal testing. So we're going through this testing phase at the moment. And so this is a schematic of what SMAR is going to look like. It's going to look down at that magnetopores and see how that's moving in and out, and at the same time look at the aurora. And so the ultraviolet aurora, as SMAR goes through its orbit, it's going to take 2 days roughly to do that. It's going to look at the northern hemisphere aurora only. So it's going to whip around the Earth and it can't take many observations, and it's going to go high up into its orbit around apogee, look down at the Earth's upper atmosphere and really see that aurora oval. And we see how that changes as conditions in the solar wind change out in space. So we've got this ultraviolet aurora and we've got these X-rays. So we do simulations of these X-rays, so we model what we think we get. This is kind of the emission. This is a model at the bottom image here of what we'd expect in X-rays through that solar wind charge exchange process. If we run it through an instrument simulator, we'll get something like this. Now you might think, well, that is rubbish. This is actually what the X-ray telescope is going to see. It's not very good. But for X-ray astronomy, this is actually pretty good. We don't get very clean precision images, nothing like you're getting from James Webb at all, nowhere close, very grainy, but we're grateful for the photons that we get. So this is what we model, and this is what we think we're going to see. And with those X-ray images, this is a case of when the solar wind is going to be really strong, where maybe the densities are really high or the speeds are really high, or maybe we've got lots of oxygen, and we get the image from the X-ray camera, the SXI on the right. And this is how we got our logo. I don't know if you can see this. So we switched this on the side. You can see we got the logo from SMAR from one of these modeled emissions from the X-rays. It took a long time to design the logo. And if we know the solar wind is highly variable, so we'd expect sometimes we're not going to get very many X-rays at all. So in the case that we don't have many X-rays, in the bottom panels, you can see that the emission is less bright, and therefore we're going to get a worse image with our X-ray camera. But even so, you imagine you look out your window, you look across your room, and you can imagine you can't get to the other side of the room. All you can do is take a photo of it. You've never been there. What is that thing that you're looking at? You know it's a 2D image, but you know it's a 3D structure. So we have to try and understand that 3D structure. We get something like this, and how do we get a 3D structure out of that? Now, there's two methods that we can do to try and make this into 3D. We can move along the orbit of SMILE and take multiple views. So this is a bit like doing a tomography in a hospital. You know, a camera moves around an object, and little by little, it can make up a 3D image of that object. Now we can do that with SMILE. As SMILE moves around its orbit, it's going to take multiple images of the magnetopores. Well, that's okay, but we know the magnetopores moves. and the SMART is going to take 2 days to take that, to do the whole orbit. So it's not going to be a really good representation of where that magnetopause is. It's going to be moving all the time during that 2 days. The other thing we can do then is model from one image, model solutions. So we can try and make a fake magnetosphere and see which one would give us the best copy of what we've just taken the photo of those X-rays, and see if we can get our best model that matches what we're seeing from our X-ray camera. And eventually we'll be able to describe that magnetopause using a couple of parameters, a couple of angles and a couple of distances, and that will give us that shape and the position of the Earth's magnetopause. But SMART could really give us more. So we've got these two imaging cameras on board, the X-ray camera and the ultraviolet camera, and they'll have two in situ, I shouldn't leave those out, two in situ instruments as well, measuring the magnetic field and also particles around the spacecraft. But it could do even more if it used different experiments on the ground. So this is what my work is involved in at the moment, using those radar, using there's changes in the magnetic field. The map below shows you where we're measuring the magnetic field of Earth. We've got this radar that you can see in the snowy pictures looking up into the atmosphere. And in the top right, you can see a camera that's sitting down on the ground looking and getting a horizon to horizon view of the sky. Now this will give us a more detailed view of what's happening in the aurora. So that ultraviolet images is going to tell us about 100-kilometer scales. If we want to look at meter-kilometer scales, we really need to use different equipment. So those auroral cameras that were on the ground looking up might give us something like this. And you can see this over the Northern Hemisphere, the North American sector, over Canada and Alaska. You can see that this is a composite of many different of these type of cameras joined together to see what is happening at kilometer or tens of kilometer scales in the aurora. And this is from a different, not for SMAR, but hoping to do something similar for SMAR with these sort of cameras. So we can look at the large scale phenomena using the SMAR spacecraft and use ground-based equipment to look at multiple scales from the ground looking back up into space. Now, SMART could give even more if we have more spacecraft. I know it sounds a bit demanding, doesn't it? Can I have another spacecraft, please? But this is what we are trying to do at the moment. Now, there are a few projects that have been considered, have been not selected by the other space agencies. And one, we have colleagues in the US who are hoping to put a camera back on the moon. So like that magic idea we had back in 2007, they're hopefully going to put something called Lexi back on the moon and look back at the Earth system. So that would give us this tomography instantaneously. So that's the real power of having more spacecraft at the same time. We'd be able to do this tomography like that. So hopefully we'll have some missions working in parallel with the SMILE. So we recently heard that one of these missions didn't get selected. That's the orange one with the two in the top right. And hopefully that Lexi to go back to the moon will happen 2024-ish, and that's a NASA mission. So SMILE is being prepared by a massive team of people, and this is a small selection of that team. I just want to say to that team, thank you very much. You're a great bunch to work with, miss you, and it's been a long time, but hopefully we'll get together in person soon. But we're working with people all across the globe, from China, Europe, America, Canada, and they're a real great bunch to work with. So I hope I've convinced you that using these images is going to give us this real novel view of what's going on in space and space weather. It's going to shift our understanding from just taking these point measurements that we have at the moment and getting these images of the Earth system. So it really is a new era for our understanding of geospace. And I'd like to finish up by Caroline's journey through space weather. So Caroline, as we started our lecture, found that space weather was a problem. But we jump a couple of years, and so now in 1795, Caroline finds that I have been looking at strong and beautiful Aurora Borealis. They expressed all the colours of the rainbow very distinctly. So she ended up by finding out and appreciating space weather for the beauty that it gave. So I think that's a nice journey, and I think that's how we can think of space weather now. So thank you very much for listening, and I hope you've enjoyed this trip through how space weather can be a problem, but it also can be very beautiful. Thank you.
Thank you so much. That was absolutely fascinating. I've been a planetary and plasma scientist in my time, and I think a tool like SMILE would have been fantastic when I was doing my magnetopause calculations at Saturn. So, like you said, the aurora is a brilliant link between the sun and the earth, and it's really good for public outreach as well, isn't it? I think making the public understand that the sun and the earth are intrinsically connected. And I know you like to do a lot of public outreach, and what sorts of things have you found yourself doing other than Tai Chi in your time?
Oh yeah, so Tai Chi is great, so you can all remember that forever and part of your daily exercise regime. So with the aurora, I mean, with young children, I talk about Frozen. So the aurora pops up in a couple of popular, movies that we have out there, and it's in a couple of songs, so I can sometimes hear it, go, oh, Northern Lights, someone's mentioned the Northern Lights. So there's lots of popular references, so that's good to get people involved. We look at using fluorescent tubes, things that, plasmas that we have here on Earth. We talk about plasmas being, plasmas in the solar wind is no different from the plasmas you may have in a fluorescent tube in your garage, for example. So we talk about the similarities between that, connecting what's going on in space with, real examples that we have here on the ground.
Yeah, and I think that's fantastic. I was telling my mum the other day, well, trying to explain to her why all those beautiful aurora that people have been seeing in Scotland recently weren't visible from London. So I did draw a few pictures. I didn't reference Frozen at all with her though.
Yes, it can, if the solar wind gets really active, then they will drop down. So that's why Caroline was able to see them a couple of times. It just happened in Caroline's life that the sun was particularly inactive. So there weren't many cases where she could have even seen them. She was lucky she had dark skies. We struggle with that, right, in the south.
I think it's amazing that you can actually, I mean, one of my most favorite things at the RAS is Caroline's notebooks, and her handwriting is so perfect that you can read exactly what she observed. And I think that's amazing that you can trace back to then and link all that together now as well, which is really, really brilliant. So a few questions. Just to start with, just for a record that the SMILE instrument is UK funded by the UK Space Agency and not ESA, apparently. I just didn't realise.
So, well, SMILE as a whole is an ESA, Chinese Academy of Sciences mission, and then the UK is UK Space Agency is funding the soft X-ray imager. Wow. So, which is the X-ray camera. Yeah, it's putting in about 12 million pounds, I think, into the development of the camera. And that is being led by the University of Leicester. We've got Mullard Space Science Laboratory, the Open University, RAL Space. So there's very different partners across the UK. And so, yes, there is a big funding that's coming from the UK Space Agency.
Right, so that's from Chris, thanks for that. So from Terry, thank you very much for a great talk. Are we headed for an average solar maximum this cycle, or lower or higher?
Oh, I don't know. I think the jury's still out on there, and I think people got very excited this week about the CME that we saw from the picture from Shetland. And I saw some comment that it looks like things are kicking off. What I did hear was that this solar cycle is most likely to be like or near identical to last solar cycle, which wasn't particularly exciting. But you also hear that CMEs, these big clouds, can happen at any time, regardless of how low the activity is in general. So you could have, on top of a very sort of standard, boring, quiet solar cycle, you could have some very, very dramatic events. So one doesn't preclude that it doesn't eliminate that possibility of happening at all.
Brilliant, thank you. Excellent talk by Jennifer. Will these advances help us on Earth to predict more accurately inbound bad space weather that will damage technology in orbit on the ground on us?
Yes, I hope that the results from SMILE, so understanding how the magnetopause reacts, how it moves in, how this reconnection happens on a large scale, will help us improve our models of that reconnection. And so understanding our results will then feed into models of making better predictions, so we can do nowcasting and then forecasting of space weather. So the idea is that you get this forecast like you get for terrestrial weather. You say in a couple of days' time, we expect, with a high degree of accuracy, we'd expect this to happen in our atmosphere. So that's what we want to get to, a really good, strong forecast.
Would you work with, say, the Met Office for something like that then?
Yeah, so the work I do is we work closely and we collaborate with the Met Office. Or we speak to the Met Office, I speak to them. We work through, scientific processes of going through conferences and talking about our results and feeding into each other. Now, there are large programs in the UK. One's called Swimmer, about improving forecasting and the tools that we have on making our space weather forecast better. So looking at how satellites have drag, atmospheric drag. So Elon Musk had this problem, right, a couple of weeks ago. He lost. So people are looking into making those predictions better about when the atmosphere swells up in response to space weather events, then increased drag on satellites, for example, or how this affects radio communications. So there's lots of effort that going in with many different universities across the country looking into this.
Brilliant. And then a question by Ted. Would it be possible to see the X-rays in a CME before it arrived at Earth's orbit by looking in the right direction?
Well, that is a good question, because we're seeing those X-rays because the solar wind plasma is interacting with hydrogen, neutral hydrogen. Now, we have neutral hydrogen around the Earth, but we also have neutral hydrogen and helium across the whole of the solar system. There's not much, but there is enough to make detectable emissions. Sometimes you have to integrate those emissions for a long time. So you're taking 15 minutes, 20 minutes, looking in the same space. It's not like a quick photo. So yeah, you could do, if you were lucky and you had very bright emissions. It would be difficult to do in the heliosphere, in the bigger solar system, to track the coronal mass ejection. The most effective way to do it is the missions that we have at the moment. SOHO, looking at that, the CMEs using ultraviolet light and tracking them properly. The X-rays are useful when we get to Earth because we have much more hydrogen around the Earth and it gives us a better signal. So we need to, there's not many X-rays. We have to always collect as many as possible and integrate for a long period of time. So the best place to look at those X-rays is in the Earth's exosphere.
And then a few more questions, if that's okay. The first one, is it possible to generate energy from solar wind?
Well, what's happening is there's the energy from that solar wind. It is coming into the Earth's atmosphere. So we call this dual heating. So those particles coming into the atmosphere, they are heating up. They're coming in, they're hitting our atmosphere, they're making it glow. So there is a transfer of energy into the upper atmosphere. It's not useful in terms of we can't. Transferring that it's little bits in large areas, but collectively it's a lot of energy on the whole. You're talking about hundreds and thousands of kilometer scales. So there is energy and heating that happens that could be 20% of the heating I've seen in the upper atmosphere could be due to these particles coming in and having, say, protons colliding with our upper atmosphere, neutral atoms in our atmosphere. And localized, it can be really hot, so it can make heating in very small localized regions.
Well, we can't use it as a sort of...
No, I can't imagine a scenario where, I can't imagine that off the top of my head right now. Where that would be useful given the small numbers in small regions and the inefficiencies, but it does heat our atmosphere, yes.
Two more questions, if that's all right. So just as the interaction between the Earth and the Sun, is the Moon also affected by the Sun's solar wind?
Yeah, well, actually, yes, because the Moon, although we don't think of it as having an atmosphere, it does outgas. I think it's argon is the primary gas there. So argon is seeps out of the rocks of the Moon, and that argon can interact with the solar wind. So instead of the hydrogen at Earth, it'd be the argon in the lunar sort of atmosphere-ish. And so we do predict X-rays, a small amount of X-rays from the lunar around the lunar atmosphere. Not as much, but there will be some, yes.
Brilliant, thank you. And the last question that we've got time for is, how long is the SMILE mission going to be?
Well, nominally we get 3 years. We're hoping the maximum given engineering constraints, is 7 years. So if we launch in 2024, we will hopefully cover the next solar maximum, which is a great time because then we get more CMEs, more dramatic events to look at. You get a couple of years from the agencies, and then you ask for an extension, you may get another couple of years, but 3 to 7 years is what we're looking at.
Brilliant, thank you. There are a few other questions. I'm sorry we haven't had time for them all today. And there's also lots of thank yous, great talk, thank you, fascinating, first class presentation. So we thank you again, Dr. Carter, that was absolutely fascinating. A really interesting topic for a Tuesday afternoon, much more interesting than my lunch, that's for sure. Thank you to the audience as well for being with us. We will have more online public lectures coming up, so do keep an eye on our websites and on Eventbrite for future lectures. Thank you again, Dr. Carter, and we'll see you again.
Thank you for having me. Thank you for coming, everyone.